Hi, this is Dan Bullard, retired electronics engineer, sitting on the front deck of my houseboat. It's a beautiful place. You can see behind me, it's lovely. I want to talk about harmonics, but this time harmonics of a square wave. Okay. Mostly I deal with harmonics of sine waves with distortion, but I want to talk about where this came from. I figured all this out by going back to square waves. Now, with square waves, there's a thing called the Taylor series. And the Taylor series helps you determine the harmonics that are in a square wave, but only a 50% duty cycle square wave. The 50% duty cycle square wave has only odd harmonics, no even harmonics at all. And that's because they cancel each other out. Okay, that's my theory. You don't have to believe me, but that's the way I look at it. It works better if you think of it that way. Now, if you change the duty cycle, what's the harmonic signature going to look like? Well, that was a question posed to a place called Analog Heaven. And this guy said, does anyone know the formula for calculating the resulting harmonics of a pulse wave when the pulse width is varied? The guy who founded Analog Heaven, David Hallel Wilson, answered the question, and he said he found it in Sham's Outline Series, Mathematical Handbook of Formulas and Tables. So in that book, they had a formula, or they at least had some information, and he was able to work out the formula. Now, it turned out that I volunteered for the Vancouver Community Library at the time. And so I was able to get my hands on that book, and I verified what he found, and I looked at his formula, and it made sense to me, so I used his formula. If the duty cycle is exactly 50%, then you'll get only odd harmonics, and you get this really cool pattern. But if the duty cycle changes, this formula will figure out what the humping pattern will look like, and it does hump just like sine waves with distortion. And you get some really interesting stuff. Do you know what happens if you change the duty cycle to be 0.0001%? You get a flat line, an absolutely flat line. Now, some people have been tempted to use that to test a filter, okay? I was in the test business. Some of the guys that I worked with, they want to test filters with an impulse. But you can't do that. An impulse has no energy. So you shoot the impulse at the filter and it just swallows it up, and all you get is noise. It's not very helpful at all. So I found another way to do it, and I wrote an article about it called, it's on periodic white noise. It's called, It's All in the Noise. I think it was in engineering evaluation or something like that, one of those magazines. So that's a better way to go, but it is interesting. And if the duty cycle is 99.99999%, you get an impulse going down, and that again gives you an absolutely flat response. So based on those two things, you can figure out the formula. Okay, and David Hallel Wilson did come up with a formula for that. And I have to credit him with that. Unfortunately, he died at a relatively young age. Very sad. But also the guy who asked the question died relatively soon after that, which was kind of sad. But the formula did help me come up with a way to solve for distortion in a sine wave. The problem was David Hallel Wilson only took it to the first hump. He didn't go beyond that. If you go beyond that, you find out that using his formula, you get a negative magnitude. Now, spectra don't have negative amplitudes, right? They're magnitudes. The value in there is a magnitude of the wave. So any wave is considered positive and negative. It goes up and it goes down. So there is no sign. So I had to use the absolute function to cancel the sign, but I did it, I figured it out, I got it, and from there I was able to go get the rest of them. So it's really cool. I mean, the fact that, Square waves and triangle waves work kind of similar in that way, and they're just special cases of distortion. And so chapter 2 of this book, Harmonics and Distortion, chapter 2 covers both square waves and triangle waves, and it gets you to understand what's going on, especially with the even harmonics. So I really encourage you to read that. And you don't have to read it. If you look at www.danbuller.com, you'll find all my articles, and I've written a number of articles about how even harmonics cancel out and how I figured out the distortion formula and the whole thing. So take a look. It's there. It's available. It's free. Or you can buy the book. Whatever. It's okay if you don't want to buy the book. That's fine with me. I give away a lot of them, but don't write me to ask for a book. You want an autographed copy? It'll cost you, okay? Anyway, this is Dan Bullard from the river, signing off.